Okay, where were we? Okay, and then I showed last time that going from here to here, because we know that the normal acceleration is always pointing inwards towards this vector, a sub n always points this way, then we can just get the magnitude with omega squared times the magnitude of r, the magnitude of this is omega squared times the magnitude of r, and the direction is the unit vector that r is pointing in. So you can just do omega squared times the r vector, the negative of the r vector, to make it pointing downwards. But what I've heard a lot of students struggle with is this equation is a vector equation. Every term in this equation should have an I hat and a j hat attached to it. What I've heard is for the negative omega squared r b with respect to a term, a lot of people just put the magnitude of r and the magnitude of omega here, and they just do like, I don't know, 5 squared times 1.5, and they just have that. There's no I hat or j hat, but you need a direction here because this is a vector equation, and this equation is actually 2 equations here for 2 dimensions. It's all the terms that are I hats are equal on each side, and all the terms that are j hats are equal on each side. So make sure you're writing 2 equations here when you get all your I hat and j hat terms, and that this guy is not a magnitude, this guy's a direction. And then this is just another overview that you can do the same thing with your acceleration equations from kinematics that are linear, where that guy's ADS equals v dv, and that just becomes alpha d theta is equal to omega d omega. You can also apply your constant acceleration equations if the acceleration is constant to angular equations. So on your midterm, you guys had a plane going like this, and it was decelerating with a negative a here. It was going around a curve, but you could still use your linear v acceleration equation. V initial squared is equal to v, or v final squared is equal to v initial squared plus 2 delta x times a. You can still use this even though it's going around a curve. And that's what I'm trying to show here. This is just in angular terms instead of total acceleration. But just remember that you can still use those. And then this is going to be the problem we're doing today. You guys might remember that we actually did this on Wednesday using instantaneous centers, and it made it pretty straightforward in terms of the math. Like figuring out how to do the instantaneous center might be difficult, but the algebra is a lot simpler. So today I'm going to show you guys how to do it algebraically with this equation. And we're going to do that first, and then to get these omegas, and then we're going to do the acceleration equation that I showed on the previous slide to get the angular acceleration of each of these links. But in order to do that, you have to get your omegas first. So I'm going to split it into 2 parts where we get the omegas, and then we're probably going to take like a 5-minute break and then do the alphas, because otherwise it's just way too much algebra all at once. Okay. So the first thing we know is that we're told that length BA rotates clockwise, right? And that's everything we're given besides the geometry, and then they're asking us to find angular acceleration of both of these rods. And like I said, we need to find the omega of these lengths first. Does anyone know what the velocity of B is going to be? What direction is it going to point? Straight up. Straight up, yeah, because it's just half. But just to show you guys how you would get that, because we're going to do the same thing for this guy, and it's going to be a little trickier. So to kind of get an intuition of it, if we do link AB, we will get VB is equal to VA plus omega AB cross R, B with respect to A. And R, B with respect to A is this, is equal to negative 0.175 I hat. It's going to the left, so it's negative. Coordinate system, I forgot to write that. So this is our first R vector. VA is 0, because it's just this point here. So it's just attached to the wall. So VA is 0, and we get that if you don't know the omega, you can always just assume that it's positive K, and then do your cross product, and you'll get your sign of it later. But in this case, we know what omega is. It's a negative K, and this guy is a negative I hat. So if we do our right-hand rule, I, J, K, and this is the positive direction, then we're doing K, a negative K cross a negative I. And since we're going in this direction, it's going to give us a positive J hat. So we will get that this is equal to VB is equal to, this omega is 10, right? So 10 times 0.175 is going to be 1.75 meters per second J hat. And that's exactly what we said it should be, pointing up in the J direction. So that was link AB, and again, this is the kind of method you guys should go about solving these problems, is just going link by link, writing one equation for each link, just like you guys did for nodes in trusses in statics. So link BD is next. And we already know VB is equal to 1.75 J hat meters per second. So it's probably best to write the velocity of B for this link, since we have the velocity of B here, instead of going this direction, because then we can just set this equal to the velocity of B equation for this guy equal to this, and then solve. So BB is equal to BD plus omega BD cross RBD, and RBD is pointing this way. And this BD we don't know yet, but we do know R, we don't know omega yet. So we can just substitute values in and get 1.75 J hat is equal to VD plus so we're going to get this omega BD cross this R BD, I put this wrong. B was this with respect to B, or with respect to B. This omega We don't know it yet, but we're going to assume that it's a positive k. So I'm going to assume that this guy's a positive k. If we get a negative number in the end, that means our omega is just counterclockwise. This guy, what direction is r, b, d? Positive j hat, right? So cross positive j hat. If we look at this guy, k cross a positive j is going to give you a negative because we're going this direction. So you get negative 0.2 times omega b d I hat, where this is just the value, the numerical value of omega b d. So we have this equation, and like I said before, this is two equations here, one for I hat, one for j hat. So we can just write those two, and I'm going to number them. Equation 1 is 1.75 j hat is equal to v d j hat, the component of the velocity of d in the j hat direction. And then equation 2 is going to be 0 is equal to v d I hat minus 0.2 omega b d I hat. Does this make sense how I got these two equations? This 0 is just because VB doesn't have a I hat direction, instead of just moving upwards. So we got those two equations. Now we're going to do the last link DE. And that equation, we are going to write which direction. Ultimately, it doesn't really matter which direction you choose to go for your relative velocity equation. It just, you'll get things on different sides of the equal sign. But I chose to go this way. This is R, D from E. So we're going to write VD is equal to VE plus omega DE cross RDE. And VE is just 0, right, because it's just pinned here. So this omega DE, we're going to do the same thing with this guy where we assume that it's a positive K. Assume. And then this guy, we need to find out what this is. So does anyone know what RDE is in this case? What's the first term? What's the I hat term?
Negative 0.275.
Yeah, negative 0.275. And then the J term is just 0.075, right? And so if we need to do the cross product of this guy. We can't do this little trick here where we just say, oh, I cross J is equal to an I, or yeah, I crosses J is equal to a K, or K crosses J is equal to an I, because we have two components of this R vector. So we have to actually do the determinant of this matrix where we have I, J, K, and we get 0, 0, omega DE. And then R is negative 0.275 and 0.0750. If you do the determinant of this, I'm not going to go through doing it, but if you get this, then you get negative 0.075 omega DE I hat minus 0.275 omega DE J hat for the cross product of these guys. And this goes here. So we get our next two equations, 3 and 4, which are BDI hat is equal to 0.075 omega DE I hat, and BD J hat is equal to negative 0.275 omega DE J hat. So now we have 4 equations, and we can solve for our unknowns. We don't know what BDI hat is, or omega DE, or omega BD, but we can solve with all of these. It's just a matter of substituting into them. I'm just gonna write them out for you guys instead of going through all that algebra. But you get that omega DE is equal to negative 6.364 K, and omega BD is equal to 2.39 K, and these are in radians per second. And this negative here means that omega DE is rotating clockwise and BD is rotating counterclockwise. So that's something that can be kind of easy to mess up, is when you're assuming that this is a positive K. You need to remember to carry that sign all the way through, that positive sign all the way through, until you solve for it in this last step. And when you solve for it, you get this negative sign. That means it's just the opposite. But you don't want to double count for that. It's kind of easy to do that. But if you guys do a few homework problems, you should feel comfortable with that. So that's the first part of the problem. I'm gonna take 5 minutes, erase this, and set it up for the second half. So go think about something else for 5 minutes, or go to the bathroom, or whatever you want to do.